Okay, let's dive deep into the silent workhorse of every network, the switch. We are tackling the foundational steps, really, of configuring and securing these essential devices. This is about moving well past the default, the out-of-the-box settings to establish absolute control, verifiable access, and robust security right from the ground up. If you manage network infrastructure, well, knowing this stuff is just non-negotiable.
That's absolutely right. Our sources provide a pretty targeted breakdown of basic management features on a Cisco switch. We're focusing on everything necessary to move from, frankly, a physically vulnerable device to one that is remotely accessible and, securely locked down.
Okay.
This includes core login security, transitioning from those shared passwords to per-user accountability, and implementing the required IP configuration to enable encrypted remote access, specifically via SSH.
Right. And before we even start typing commands, I think we need to understand the fundamental architecture we're actually protecting here. Everything a switch does is kind of segmented into 3 functional planes.
Precisely.
Yeah.
Yeah. If you imagine the switch as, say, a busy highway interchange, the data plane is like the high-speed traffic just moving through it.
Yeah.
That's the forwarding of frames based on the MC address table. It's all optimized for speed.
Got it. Just moving packets.
Exactly. Then you have the control plane. Now, this is more like the intelligence or the rule book for that highway. It handles processes that control how the data plane works. So this includes critical functions like running spanning tree protocol, STP to prevent network loops, or managing dynamic routing protocols if it's a layer 3 switch.
Yeah.
It basically makes decisions about the network structure itself.
Okay, makes sense. And the third plane, the one we are really focusing on locking down today, is the management plane. This is your point of entry, right? It's where protocols like Telnet, SSH, and your physical console CLI access live. This is the human interaction with the device's OS.
And here is the first and honestly pretty shocking security vulnerability by default. The physical console port is just wide open.
Wow.
Yeah. A user can literally connect a cable and reach enable mode, that's the privileged execution mode, with absolutely 0 security checks. No passwords needed at all.
So anyone can just walk up and take over?
Physically, yes.
Yeah.
Now, Telnet and SSH are usually disallowed by default, which is good, but physical security is obviously key. But immediate console protection is essential because, well, that console port is the ultimate bypass if someone gets physical access.
Okay, so immediate step number 1. Throw up the simplest protection using shared passwords. We have, 3 basic configurations for access control here?
That's right. The first 2 are pretty straightforward,
Yeah.
securing your lines of access. We configure the console password under the line console 0 configuration mode.
Okay.
And then the VTY password, which is for remote access like Telnet or SSH, underline VDT 015. That covers lines 0 through 15 usually.
Got it. Line secured. What's the third?
The third, and arguably the most critical, is the password that protects privilege mode itself, the enable mode. This is where you actually configure the device. Now, if you use the older command, enable password, that password is, well, only weakly protected. It's stored as type 7 reversible encryption right there in the running config.
Weak is not good. Okay, so if you take just one piece of foundational security knowledge away from this segment, it's this distinction right here. Always use the global configuration command enable secret password value. For instance, something like enable secret love.
That is the crucial pivot. Absolutely. The enable secret command uses type 5 hashing, typically MD5, or sometimes a stronger algorithm depending on the iOS. This means the password is stored securely and cannot be easily reversed, unlike that older type 7 encryption.
Right.
That single command instantly makes your configuration file much, much safer if it, falls into the wrong hands. Our sources show the user experience clearly. In example 6-1, they type, say, faith for the console password, and then enable, followed by the securely stored love password to actually enter privileged mode. And of course, those passwords don't show up when you type.
Right. They're hidden. Okay, so we've added basic security, but these shared passwords still present a huge operational problem, don't they? I mean, if everyone knows the enable secret is love, accountability is basically non-existent.
Exactly.
And if staff leaves, or heaven forbid, a password gets compromised, you have to push that change out to potentially hundreds of switches. Nightmare.
It really is. And this immediately raises the question, how do you actually tie a configuration change back to a specific person for auditing? The answer is moving to local usernames and passwords.
Oh, okay.
You configure unique per-user pairs directly on the switch itself using the global command. Something like username Wendell, secret Odom.
Okay, so username, then the name, secret for security, then the password.
Precisely. Then, to tell the switch to actually check that local list instead of just asking for that single shared password on the line,
Yeah.
you replace the simple login command on the console or VTY lines with the far superior login local line subcommand.
Login local. Got it. And this is where the operational benefit really hits home, I imagine. Our sources example 6-4 shows a user logging in via Telnet, all right? And subsequently, the switch logs a message that explicitly states, configured from console by Wendell on VNA 0. That's the audit trail you absolutely need. It links the action directly to a specific user identity. Accountability.
Exactly. And if we zoom out, look at the bigger picture for large-scale operations, even configuring local usernames on dozens, maybe hundreds of switches becomes pretty tedious.
Yeah, I can see that.
That's where the gold standard comes in. External authentication utilizing AAA servers.
Right, AAA. Authentication, authorization, and accounting. Can you explain briefly why, beyond just saving time configuring users everywhere, centralized AAA is so necessary for a robust network?
Well, the security and, frankly, legal implications are enormous. Centralization simplifies administration, sure, that's a big plus. But more importantly, the switch essentially delegates the whole login process. It sends requests using protocols like Radius or TACAS Plus to a specialized server.
Okay.
This means you can implement things like mandatory multi-factor authentication centrally. You can ensure rapid credential revocation across the entire infrastructure instantly if someone leaves or is compromised.
Oh, that's huge.
And crucially for compliance in many industries, the accounting function tracks every command run by every user. This creates non-repudiable audit trails, which are often mandatory in regulated environments.
Okay, so AAA is definitely the way to go for serious setups. We've solved who is logging in. Now let's solve how they are logging in securely. We absolutely need to ditch Telnet, right?
Oh, absolutely. Telnet has a fatal flaw that has, well, plagued networks for decades. It transmits all data, including your precious passwords, and every command you type in clear, unencrypted text. It is. Anyone sniffing the network traffic, maybe via a simple man-in-the-middle attack, can just grab your administrative credentials instantly. Game over.
Which means we embrace SSH, Secure Shell. SSH encrypts the entire session end-to-end between the client and the switch. And importantly, this requires us to use username authentication, meaning those older, simple shared VTY passwords won't cut it anymore for SSH. You need login local or AAA.
Correct. Now, setting up SSH requires 3 essential configuration steps, and they all kind of center on generating strong encryption keys. SSH relies on the device having a fully qualified domain name, an FQDN, to achieve this key generation.
Right, and I can hear people listening thinking, wait, why do I need a domain name just to log into a switch sitting in the corner? That seems like maybe overkill.
Yeah, it sounds a bit weird at first, but it's necessary because the FQDN serves as the unique identifier used by the switch's cryptographic module when it generates the keys. So first step. Set the host name. Let's say hostname 701. Simple enough.
Okay.
Second step, define the domain name. For example, epdomainnameexample.com. Once the switch knows its full identity is sw1.example.com, you move to the third crucial step, executing the command crypto key generate URSA.
Crypto key generate URSA, and that kicks off the key creation.
Exactly. It generates the required public-private key pair. Now, a critical security note here. You must specify a key size large enough to ensure SSH version 2 is used. The current best practice minimum is generally considered 768 bits, but really, you should probably aim higher, maybe 124 or even 2048 bits. Older, smaller key sizes are definitely vulnerable these days.
Good tip. Okay, keys generated. Now we revisit the VTY lines, those virtual terminals, to control access explicitly, and that's done using the powerful transport input command, right?
Correct. This command, used within the line Vano Vera15 configuration mode, determines exactly which protocols are allowed to connect remotely. You have options like transport input all, which dangerously allows both Telnet and SSH.
Not ideal.
No. Then there's transport input none, which blocks all remote access entirely. Might use that sometimes.
Okay.
Or the preferred secure option, transport input SSH. Only allow SSH.
So even if the default setting on a particular iOS version might happen to favor SSH, if we're focusing on really hardening the device, the best practice is always to explicitly configure transport input, SRESH. Just nail it there.
Precisely. Explicit configuration removes any ambiguity, any doubt about defaults changing in future software versions. Always be explicit with security settings.
Makes perfect sense.
And once you've configured it, you can verify that the SSH service is running and configured correctly using verification commands like show ipsesh and show swash. Those will confirm the status and show any currently connected clients.
Excellent. Okay. Now, all this advanced security is kind of a moot point if the switch can't actually communicate over the network in the first place using IP. For any remote management SSH, Telnet if you must, WebUI, SNMP, the switch needs its own IP address.
That's right. And importantly, that IP address is for management traffic only. It doesn't live in the data plane where user frames are forwarded based on mass addresses. It's really part of the control plane functions used for managing the device itself. Now, since a typical Layer 2 switch is fundamentally an L2 device, it doesn't have physical Layer 3 interfaces like a router does.
Right. Which brings us to that conceptual oddity. How do you give a Layer 2 device a Layer 3 identity, an IP address?
We use something called a switch virtual interface, or SVI. You often hear it just called a VLAN interface.
Yeah.
Think of the switch maybe as an apartment building that's Layer 2, handling internal deliveries between apartments based on room numbers or AMC addresses.
Okay, good analogy.
But for the building manager to receive mail from the outside world that's your management traffic, they need a specific mailing address, which is the Layer 3 IP address. The SVI is essentially that address for the switch itself.
Ah.
And a Layer 2 switch usually only needs one management IP address, typically configured on the default VLAN 1 interface just for management purposes.
Okay, so we need to statically configure this SVI. Let's walk through the, 3 commands required.
Yep, 3 key commands. First, you enter interface configuration mode for that virtual interface, interface LAN 1.
Interface LAN 1. Too.
Second, you assign the IP address and the subnet mask. Something like IP address 192.168.1.255.255.255.0.
Standard IP config.
Exactly. And the third, the one that is so frequently forgotten and causes so much troubleshooting headache,
I bet I know this one.
is no shutdown.
Knew it? No shut.
Yeah, no shut. That command is absolutely crucial to administratively enable the interface. They often start in a shutdown state by default.
Yeah.
You have to bring it up.
Right, and even with the IP configured correctly and the interface up, the switch might still be kind of blind to the outside world, right? Why is the default gateway configuration so essential here?
Because the switch, by default, only knows how to talk to other devices on its immediate local subnet, the 192.168.1.0 network in our example. If you were trying to manage the switch remotely from a different subnet, say your management workstation is on 10.1.1.0 or you're coming in from home over a VPN, the switch needs to know where to send the return packets.
It needs a route out.
Exactly. It needs the IP address of the router, the next hop, that can forward its management packets towards your remote location. And that's configured globally using the command IP default gateway 190.168.1.1, assuming point 1 is the router on that management VLAN.
Okay.
Without that default gateway, you could probably SSH to the switch if you were plugged into the same subnet, but not from across the rest of your network or the internet.
Makes sense. And while static configuration is definitely standard for management devices like switches and routers, the source does note you can technically use DHCP.
Yeah, you can use the IP address DHCP command within the interface config. But again, static IPs are really the norm for infrastructure devices, easier to manage and track.
Right. And you verify all this IP connectivity status using commands like show interfaces VLAN 1 and critically show IPU default gateway.
And we focused heavily on the CLI, the command line, but we should probably briefly address WebUI access too. Most modern administrators really want to disable any unencrypted management access, period.
Yeah, that makes sense. So that means we must explicitly disable the standard HTTP on port 80 and switch everything over to HTTPS, right?
Correct. The clear best practice here is to use the command no IP HTTP server. That disables the unencrypted web server.
Okay, turn off the bad one.
Then execute HTTP secure server. This enables HTTPS on port 443, utilizing TLS encryption for security.
Right.
And this actually often leverages the same RSA keys we generated earlier for SSH, kind of linking those security features together.
Convenient.
And here's a crucial little detail for anyone planning on using the WebUI for actual configuration, not just monitoring. Unlike the CLI, where a user can log in and then use the enable command to get privileged access. To access all configuration features via the WebUI, the user account itself must be explicitly configured with the maximum privilege level, which is level 15. This is done during the username creation step. For example, username admin privilege 15 secret super secret pass. You have to add that privilege 15-bit.
Got it. Privilege 15 for full WebUI control. Good to know. Okay, finally, before we wrap this up, let's talk about 3 quick productivity commands. These are the quality of life adjustments that honestly save you time and massive frustration, especially when you're practicing this stuff in a lab environment.
Oh yeah, these are lifesavers in the lab. The first one is simple, preventing those irritating syslog messages from interrupting you right when you're typing a command.
Ah, I hate that.
Right. You're typing a long command, a log message about an interface going up or down, pops up right in the middle, breaks your flow. That's frustrating. The fix is the logging synchronous command, applied in line configuration mode, console, and Filey. It basically holds the message until you hit enter or the command prompt returns. Much cleaner.
Brilliant. Okay, second one.
Second is a lab essential, but please, a production hazard. Disabling that annoying 5-minute inactivity timeout.
Oh, yeah. I've lost count of how many times I stepped away to grab a coffee, came back, and my session was disconnected. Lost my place.
We've all been there. Use exec-timeout 00 inline configuration mode, console and VISI. The 00 means 0 minutes, 0 seconds, basically, infinite timeout.
Perfect for the lab.
Perfect for the lab. But seriously, never, ever use that in a production environment. That's a security risk.
Definitely noted. Okay, and the third productivity hack.
And the third command saves you maybe 60 seconds of pure agony every time you mistype something at the command prompt. If you forget to type show first and just type, say, interface VLAN 1, the switch interprets interface as a host name you want to telnet to.
Oh, right, and then it just hangs.
It hangs. It initiates this lengthy, agonizing DNS lookup process, trying to resolve the name interface, causing your entire session to freeze until it times out.
So painful when that happens. What's the fix?
The fix is instantaneous and, frankly, mandatory for efficient work. Use the global configuration command, no if domain lookup.
No if domain lookup.
Yep. This immediately tells the device, stop trying to resolve mistyped commands via DNS. Huge time saver.
Okay, that's a great list of practical tips.
So just to summarize our deep dive here, we basically transitioned from that initial state of basic physical vulnerability to achieving robust remote security. We established the critical importance of moving to per-user accountability, whether that's local authentication or, ideally, centralized AAA. And we locked down that remote access using SSH, making sure that the prerequisite SVI configuration and the default gateway settings were complete and correct.
Yeah, a really solid foundation. So what does this all really mean at the end of the day? I think it underscores that the management plane security really underpins everything else. And understanding the nuances of how the switch stores this security data is paramount. We mentioned earlier that enable secret is fundamentally more secure than the old enable password.
Right, because the secret uses type 5 hashing, like MD5.
Right.
While the older password command uses that weak, reversible type 7 encryption.
Exactly. And this leads us to a final, maybe provocative thought for you, the listener. If you decide to back up your switch configuration file, which you absolutely should do, that backup often contains these hashed or encrypted passwords. Knowing that the secret is strongly hashed, type 5, and the older password is just weakly reversibly encrypted, type 7, how does this difference affect your choice of backup method? Think about it. Saving that config file to, say, an open TFTP server versus storing it in a secure, centralized configuration management system.
Good point.
The difference in how those passwords are stored in the config file itself might determine whether your entire network's privileged access is compromised the moment someone just gets access to a single one of those backup files.
Yeah.
Something to definitely mull over next time you type copy running config TFTP.